Okay, we were asked to determine the solid obtained by rotating a region bounded by a quadratic, two vertical lines in the x-axis, and we're going to rotate that around the x-axis. So the method by which we're going to do this involves basically taking lots and lots of circles with radius equal to the function and stacking them on top of each other. Now what I mean by that is we all know the area of a circle. Area of a circle is equal to pi r squared. Now what we're going to do is we're going to be getting circles that rotate or have a center on the x-axis, and the radius of these circles is just going to be a particular function. So if this is x equals a, this radius will be equal to f of a. So what we can do, to start with, we have to come up with a formula that's going to give us the cross-sectional area of circles obtained at any point along this domain. So we can see that the radius is just f of whatever x is. So the area of any circle across this domain, we can say the area with regards to x is just going to be equal to pi times the function, we'll call it just f of x or y squared. So we can substitute in our y values, which is going to be equal to pi bracket x squared minus 4x plus 5 squared. Cool. So what we find when we do this is this isn't really that helpful to us, because once we come to trying to do integration later on, that's going to be quite hard to do. So what we're going to do is we're going to expand out this bracket by basically realizing that that's going to be equal to x squared minus 4x plus 5 times itself that's minus 4x there, and if you do this expansion, you're going to end up with pi times, obviously it's a quartic, x to the 4 minus 8x cubed plus 26 x squared minus 40x plus 25. Cool. So that is a function that across this domain from 1 to 4 will give us the area of any circle with radius equal to the function. So what we then need to do is we need to somehow stack all of the little circles, or add all of the little circles and stack them on top of each other from 1 to 4. That'll give us this nice volume of this solid. So the way we do that is by using the method of integration. So what we're actually going to do is we're going to integrate. So we're going to get the volume is going to be equal to the integral from 1 to 4 of this thing. So x to the power of 4 minus 8x cubed plus 26x squared minus 40x plus 25 dx. Okay, now because pi is a constant, what we can actually do is we can put that out the front of the integral so we don't really have to worry ourselves too much about it. So let's do that straight away. Let's get rid of that for a sec. And we'll write this as pi times the integral from 1 to 4 of this thing. So what we can then do is we're actually going to anti-differentiate the inside function here. So hopefully you're familiar with the method by which you anti-differentiate. So I'm going to just do this for you now. Oh wow, hang on a sec. Forgot to put my pi in. So we have equals pi. Now if we're going to evaluate this, we put it in square brackets. This is going to be equal to x to the 5 over 5 minus x, that'll be taken to x to the 4, divided by 4, 8 divided by 4 is 2. X to the 3, we're going to have 26 over 3. It'll be x squared, so divided by 2, so we'll have minus 20. Plus 25x, and we have to evaluate that between 1 and 4. So what this then involves is we evaluate this function that we've derived here at 4, and it'll pop out a number. We evaluate this function at 1, and it'll pop out a number, and then we subtract the one that we get at 1 from the one we get at 4. After we do all that, we then multiply it by pi. So what we find is the volume of this solid is equal to 78 pi over 5, and then we write afterwards units cubed. And that is the solution.